There was a moment before stars, before planets, even before light itself, when the entire universe was nothing but a swirling, turbulent sea of raw energy. Picture it, a realm where the laws of physics as we know them didn't yet exist, where chaos reigned supreme. How did this unimaginable storm of pure potential, give rise to the ordered cosmos we see today? It's a question that has haunted humanity for millennia, whispered in ancient myths and pursued by the brightest scientific minds of our age. And it's a mystery we're about to unravel together. Think about the world around you, the galaxies spinning in perfect harmony, the delicate balance of forces that allow life to exist. None of this was inevitable. Our universe could have remained forever lost in that primordial chaos, a place where time and space had no meaning, yet somehow, against all odds, order emerged. How? That's the story we're diving into today. From the explosive birth of the Big Bang to the delicate dance of particles that formed the first atoms, we'll trace the incredible journey from chaos to cosmos. Along the way, we'll explore the cutting-edge theories that push the boundaries of our understanding, and even glimpse the surprising connections between modern science and the oldest creation myths humanity has ever told. This isn't just a tale of the distant past, it's the story of us. Every atom in your body, every star in the night sky, owes its existence to those first critical moments when the universe chose structure over chaos. By the end of this journey, you'll see the cosmos in a whole new light, with a deeper appreciation for the fragile, improbable beauty of everything we call home. So let's begin where all great stories do, at the very beginning, when the universe was a blank canvas and the first strokes of order were yet to be painted. The moment of the Big Bang wasn't an explosion in empty space, it was the birth of space itself. Picture trillions of degrees of heat packed into a single point, smaller than an atom, and then suddenly everything. Space unfurled, time began ticking, and the universe as we know it surged outward in a fireball of pure energy. But how do we know this actually happened? The evidence is all around us. Take cosmic microwave background radiation, the faint afterglow of that initial explosion. It's like the universe's baby photo, a snapshot from when it was just 380,000 years old, still glowing with residual heat. Then there's the way galaxies are racing away from each other, a cosmic echo of that primordial expansion. If you rewound that motion like a film reel, everything would collapse back to that single, unimaginable starting point. Yet for all its explanatory power, the Big Bang theory leaves us staring into an even deeper mystery. What came before? Was there a before at all? Time as we understand it may have begun with the Big Bang, making the question itself almost paradoxical. Some theories suggest our universe could be one bubble in a vast multiverse foam, where new universes constantly spring into existence. Others propose a cyclical model, where the cosmos collapses and reboots in an endless loop. But here's the humbling truth: we may never know for certain. The energies and conditions of that first fleeting instant are so extreme, they defy even our most advanced physics. What's astonishing is how much order emerged from that chaos. Within the first second, the universe cooled just enough for quarks to clump into protons and neutrons, the building blocks of atoms. A few minutes later, the first hydrogen and helium nuclei formed in a process called Big Bang nucleosynthesis. These simple elements would become the seeds of stars, planets, and eventually us. It's a reminder that our existence hinges on a razor-thin balance of conditions. If the expansion rate had been slightly faster, matter would have scattered too thin to form galaxies. Slower, and everything might have collapsed back into a black hole. So while the Big Bang gives us a starting line, it also opens a door to deeper questions about the nature of reality itself. Was it truly the beginning, or just a transition from some other state we can't yet comprehend? The search for answers continues, pushing the limits of human curiosity and ingenuity. And as we peer back toward that first moment, we're not just uncovering the universe's secrets, we're unraveling the story of our own origins. Just when the universe was a mere fraction of a second old, something extraordinary happened, an event so dramatic it would shape everything to come. In a blink smaller than a trillionth of a second, space itself stretched at speeds beyond light's reach, inflating the cosmos from subatomic size to something vastly larger than our observable universe today. This wasn't just expansion, it was a runaway stretching of reality, smoothing out wrinkles in spacetime like a cosmic iron pressing out the primordial chaos. Why does this matter? Look up at the night sky and you'll notice something strange. No matter which direction you gaze, the universe appears remarkably uniform. Distant galaxies, the cosmic microwave background, even the distribution of matter, all eerily similar across billions of light years. Without inflation, this uniformity would be impossible. Think of it like blowing up a balloon with tiny dots. As the balloon inflates, the dots spread apart evenly. That's precisely what happened to quantum fluctuations in those first moments stretched across the cosmos. They became the seeds for galaxies and galactic clusters we see today. But here's the puzzle. What triggered this hyper-expansion, and why did it suddenly stop? Many physicists point to a mysterious energy field called the inflaton, which momentarily dominated the universe. Like a coiled spring releasing its energy, this field's decay could have powered inflation's breathtaking expansion. And when it fizzled out, its energy transformed into the hot soup of particles we recognize from the Big Bang's aftermath. Some theories even suggest inflation never truly ended, that pockets of space continue inflating eternally, spawning new universes in an endless multiverse. The most astonishing legacy of inflation lies in its imperfections. Those quantum fluctuations, magnified by inflation's relentless stretching, created slight density variations in the early universe. Over billions of years, gravity amplified these tiny differences. Denser regions pulled in more matter, growing into galaxies, while emptier spaces became vast cosmic voids. Without those microscopic ripples, the universe would have remained a featureless sea of particles. No stars, no planets, no us, yet mysteries linger. Why did inflation last just the right fraction of a second to produce our habitable cosmos? Could different inflation rates have created alternate universes with entirely different physics? These questions push scientists to probe the universe's earliest moments with space telescopes and particle colliders, hunting for faint imprints of inflation's passage. What they've found so far is both humbling and exhilarating, a reminder that the universe's grand structure hinges on events so brief they make the blink of an eye seem eternal. Imagine the universe in its infancy, a vast, empty expanse where even the concept of empty defies our everyday understanding. Beneath the apparent stillness, quantum mechanics tells us something remarkable was happening. Space wasn't truly empty at all. Instead, it fizzled with fleeting bursts of energy, particles and antiparticles popping in and out of existence in a cosmic dance dictated by the uncertainty principle. These ephemeral quantum fluctuations, lasting mere fractions of a second, might seem insignificant, but in those first moments of inflation, they were stretched across the cosmos, magnified from microscopic ripples into the scaffolding of reality itself. Here's the astonishing part: those random fluctuations became the universe's blueprint. Where slightly denser patches of energy emerged, gravity got to work, pulling matter together over billions of years to form galaxies and clusters. The emptier regions expanded into the vast voids we see today. It's as if the universe rolled a quantum dice, and the outcome determined the distribution of everything we now observe. Without these tiny imperfections, space would have remained perfectly smooth, a cold, dark, and lifeless uniformity. This raises one of cosmology's most tantalizing mysteries. Why were the fluctuations just right to allow structure to form? The margin for error is vanishingly thin. If they'd been stronger, matter might have collapsed into black holes before stars could ignite. Weaker, and gravity wouldn't have had enough to work with, leaving the cosmos forever scattered and barren. Some scientists argue this points to fine-tuning a set of physical constants so precisely balanced. It's as if the universe was designed for complexity. Others propose a multiverse where countless universes with different parameters exist, and we simply inhabit one where conditions allowed galaxies and life to arise. The echoes of these quantum ripples are still detectable today. When astronomers map the cosmic microwave background, they're essentially reading the universe's thermal fingerprint from its infancy. Those faint temperature variations, hotter and cooler spots, are the magnified remnants of those primordial fluctuations. It's a direct line back to the quantum chaos that birthed cosmic order. So the next time you gaze at the night sky, remember the glittering tapestry of stars and galaxies traces back to randomness on the smallest scale. What began as subatomic uncertainty became the foundation for everything. And in that paradox, the marriage of chaos and order lies one of the universe's most profound lessons. Sometimes the slightest imbalance is all it takes to shape reality. For all the stars and galaxies we can see, they're just the tip of the cosmic iceberg. The real architect of our universe's structure is something we've never directly observed: dark matter. This invisible substance doesn't emit, absorb, or reflect light, yet its gravitational grip is so powerful. It sculpted the universe into the intricate web of filaments and voids we see today. Picture it like the hidden scaffolding behind a grand building. Ordinary matter, the stuff we're made of, simply followed the blueprint dark matter laid out. Here's the staggering part. For every bit of visible matter, every star, planet, and speck of cosmic dust, there's 5 times more dark matter woven through space. Without it, galaxies would fly apart, their stars scattering into the void. The reason? The gravity of visible matter alone isn't strong enough to hold galaxies together. Watch a spiral galaxy rotate, and you'll notice its outer stars whirling just as fast as those near the center, defying the laws of motion unless some unseen mass is anchoring them. That's dark matter's handiwork, but what is it? Scientists have spent decades hunting for clues. One leading theory points to WIMP, weakly interacting massive particles, hypothetical heavy particles that barely interact with ordinary matter except through gravity. Then there are actions, ghostly lightweight particles that could theoretically permeate the cosmos. Experiments deep underground, in abandoned mines and tunnels, are searching for these elusive particles, shielded from cosmic interference. Others look for faint signals in space, like gamma-ray bursts that might betray dark matter's presence. The cosmic web tells the story best. After inflation, dark matter's gravity began pulling matter into dense knots, forming the first strands of the web. Ordinary matter, hydrogen and helium, flowed along these invisible channels, pooling where dark matter was thickest. Over billions of years, these pools ignited into stars and galaxies, tracing the web's pattern. The irony, the very chaos of quantum fluctuations in the early universe, magnified by inflation, became the order that dark matter would later sculpt into galaxies. Yet mysteries remain. Why hasn't any experiment definitively detected dark matter? Could it be we're missing something fundamental about gravity itself? Some theorists propose modifying Einstein's equations, suggesting gravity behaves differently at cosmic scales, but the majority of evidence still points to dark matter's existence. Its fingerprints are everywhere, from the way light bends around galaxy clusters to the precise patterns in the cosmic microwave background. Unraveling this enigma wouldn't just solve a cosmic puzzle, it would rewrite our origin story. Dark matter isn't just a passive ingredient, it's the unseen hand that shaped the universe from primordial chaos into the structured cosmos we call home. And as we peer deeper into the darkness, we're not just searching for particles, we're tracing the invisible threads that wove the universe into existence. Just when we thought we understood the universe's expansion, the cosmos delivered another shock, one that upended decades of scientific consensus. In the late 1990s, two teams of astronomers made a discovery so unexpected it earned them the Nobel Prize. They were measuring distant supernovae, using these exploding stars as cosmic mile markers to track how the universe's expansion had changed over time. The prevailing assumption was that gravity, pulling everything together, would gradually slow the expansion. But the data told a different story. The universe wasn't just expanding, it was accelerating, as if some invisible force were pushing galaxies apart faster and faster. This mysterious repulsive force became known as dark energy, and it's now the dominant player in our cosmic drama. Think of it like this. If the universe were a loaf of raisin bread baking in an oven, dark energy isn't just making the dough rise, it's causing the raisins to fly away from each other at ever-increasing speeds. What makes this so baffling is that dark energy behaves like the opposite of gravity. Instead of pulling matter together, it drives space itself apart. Even Einstein wrestled with something similar, his cosmological constant, a term he added to his equations to keep the universe static, later calling it his greatest blunder. Yet here we are, a century later, finding that his blunder might have been prophetic. So what exactly is dark energy? One possibility is that it's an intrinsic property of empty space, a sort of background energy woven into the fabric of the universe. According to quantum theory, even a perfect vacuum isn't truly empty. It's teeming with virtual particles flickering in and out of existence. Could these fleeting fluctuations generate the repulsive force we observe? Another idea is that dark energy represents a new, undiscovered field similar to the inflatoned field that drove the universe's rapid expansion in its first moments. Or perhaps it's a sign that Einstein's theory of gravity needs revising on the largest scales. The implications are staggering. Dark energy now makes up about 68% of the universe's total energy content, with dark matter accounting for another 27%. Ordinary matter, everything we can see and touch, is just a mere 5%. That means 95% of the cosmos is made of substances we don't fully understand. Even more unsettling is what this means for the universe's fate. If dark energy continues to dominate, the acceleration will only increase. Galaxies beyond our local group will eventually vanish over the cosmic horizon, their light stretched beyond detection. The universe could end in a big freeze, where space becomes so vast and empty that stars can no longer form, leaving only cold, isolated islands of matter. Yet for all its mystery, dark energy isn't entirely without clues. Observations of the cosmic microwave background, galaxy clusters, and large-scale structure all point to its existence. Even the rate of the universe's expansion, known as the Hubble constant, shows tension between different measurement methods, a discrepancy that might hint at new physics lurking beneath the surface. The next generation of telescopes, like the Vera Rubin Observatory and the Euclid Space Mission, aim to map dark energy's influence with unprecedented precision. What's truly humbling is how this discovery reminds us of our place in the cosmic story. For billions of years, gravity ruled supreme, pulling matter into galaxies and clusters. Then, around 5 billion years ago, dark energy took over, and the universe began accelerating toward an uncertain future. We happen to live in the brief window where both forces are observable, a cosmic twilight where we can still glimpse the fading embers of the early universe while sensing the vast, dark expanse ahead. Whether dark energy is a constant force or something that evolves over time could determine not just the fate of galaxies, but the ultimate destiny of reality itself. And that's a question worth chasing to the edge of the observable universe. What if our universe isn't the only one? Imagine a cosmic froth where countless other universes bubble into existence, each with its own unique set of physical laws. Some with gravity so strong stars collapse instantly, others where atoms never form, and perhaps a rare few, like ours, where conditions align perfectly for galaxies, planets, and life. This isn't science fiction, it's the multiverse hypothesis, a radical idea born from the same inflationary theory that explains our universe's startling uniformity. The logic is startlingly simple. If inflation could happen once, why not countless times? Picture a boiling pot of water where steam bubbles rise and pop in random succession. Now replace the water with space-time and the bubbles with entire universes, each pinching off from the quantum foam with its own distinct properties. In this scenario, our universe isn't special, it's just one accidental success in an endless trial and error experiment. Here's where it gets even stranger. Some versions of this theory suggest these universes could have entirely different dimensions, some with 4 spatial dimensions instead of our 3, others where time flows backward. The very constants we take for granted, like the strength of gravity or the mass of an electron, might be arbitrary lottery picks in a cosmic game of chance. That would explain why our universe seems so finely tuned for complexity. If every possible configuration exists somewhere, it's no surprise we find ourselves in one where life can emerge. But how could we ever test such a mind-bending idea? Surprisingly, there are clues. If our universe ever collided with another bubble universe, the impact might leave scars in the cosmic microwave background, subtle ripples in spacetime's fabric. Astronomers have searched for these anomalies, though none have been confirmed yet. Another approach involves studying the distribution of dark energy. If its value seems improbably suited for galaxy formation, that could hint at a multiverse where most universes aren't so lucky. Critics argue this veers into philosophy, not science. After all, if other universes are inherently unobservable, can the multiverse ever be more than a fascinating thought experiment? Yet supporters counter that good theories often outpace evidence. Einstein's gravity waves weren't detected for a century. The multiverse might simply be waiting for its technological moment. Whether real or not, the idea forces us to confront profound questions. Is our universe's order a happy accident, or is there a deeper principle at work? If chaos spawned infinite cosmic experiments, does that make existence more or less meaningful? The multiverse doesn't just expand our horizons, it shatters them, leaving us to wonder if every possibility, no matter how wild, is unfolding somewhere in the great beyond. At the heart of every atom, beneath the chaos of quantum particles, lies a radical idea. What if everything we see is made not of points, but of tiny, vibrating strings? This is string theory's bold proposition, that electrons, quarks, and even the fabric of spacetime itself are woven from unimaginably small loops of energy, each vibrating at distinct frequencies like the strings of a cosmic instrument. But here's the twist. These strings don't dance in the 3 dimensions we know. They require 10 or even 11 dimensions to make the math work. So where are these hidden dimensions, and how could they hold the key to understanding the universe's birth from chaos? Think of it like this. An ant crawling on a telephone wire sees only a 1-dimensional line, while we see the wire's full 3-dimensional shape. Could our universe be similarly trapped in a subset of dimensions, with the rest curled up so tightly they're invisible? String theorists suggest these extra dimensions might be compactified, folded into structures called Calabi-Yau manifolds, each smaller than a trillionth of an atom. Yet their influence could be everywhere. The way a vibrating guitar string produces different notes, these hidden dimensions might determine the properties of particles and forces, tuning the universe like a finely crafted instrument. This isn't just abstract math. It could solve one of physics' greatest puzzles, uniting quantum mechanics and gravity. Einstein's general relativity describes gravity as the curvature of space-time, while quantum mechanics governs the subatomic world. But when these theories collide, like at the Big Bang or inside black holes, the math breaks down catastrophically. String theory elegantly sidesteps this by treating gravity like all other forces, emerging naturally from the vibrations of strings. It's as if we've been trying to read the universe's blueprint with half the alphabet, and these extra dimensions provide the missing letters. But is there any evidence? Some predictions are tantalizing. If extra dimensions exist, gravity might leak into them, explaining why it's so weak compared to other forces. Particle colliders like the Large Hadron Collider could, in theory, produce microscopic black holes or Kaluza-Klein particles, telltale signs of higher dimensions. So far, none have appeared, but the search continues. Others look for cosmic fingerprints, subtle imprints in the cosmic microwave background, or deviations in gravitational waves that might hint at hidden spatial folds. Critics argue string theory's beauty comes at a cost. It's notoriously difficult to test, and after decades, no definitive proof has emerged. Some even call it, not even wrong, a dazzling mathematical construct without experimental grounding. Yet supporters counter that groundbreaking theories often take generations to verify. Maxwell's equations predicting radio waves or Einstein's spacetime curvature seemed equally abstract until technology caught up. Whether string theory ultimately holds the answer or not, it reshapes how we see reality's foundations. Those hidden dimensions, if real, might be the missing link between the quantum chaos of the early universe and the orderly cosmos we inhabit. They could explain why gravity is so peculiarly weak, why the universe's constants are so finely tuned, even how space-time itself emerged from something deeper. And if we ever uncover them, it wouldn't just rewrite physics textbooks, it would reveal layers of reality we've never dared to imagine. So next time you gaze at the night sky, remember, the universe's true shape might be far stranger than the 3-dimensional tapestry we perceive. Behind every star, every atom, could lie a hidden symphony of vibrating strings, playing the melody of existence in dimensions beyond our sight. And that melody might hold the secrets of how chaos gave birth to order, how a universe of infinite possibilities condensed into the one we call home. What if everything you see, the stars, the planets, even your own hands, is nothing more than an illusion, a shadow cast by something far simpler? This is the startling premise of the holographic principle, a theory so radical it turns our understanding of reality inside out. Imagine the universe as a cosmic movie screen, where the 3-dimensional world we experience is actually a projection of information encoded on a distant, 2-dimensional surface. It's as if the entire cosmos is a hologram, with every event, every particle, and every law of physics emerging from a hidden, flat boundary we can't directly perceive. This idea didn't come from science fiction. It emerged from the study of black holes. When physicists calculated how much information a black hole could contain, they stumbled upon something bizarre. The maximum amount of data it could hold wasn't proportional to its volume, as you'd expect, but to its surface area. It's like discovering that the contents of a book aren't determined by its thickness, but by the words written on its cover. This led to a staggering realization. Perhaps the universe itself obeys the same rule. All the complexity we see, the swirl of galaxies, the dance of particles, might just be information painted on the cosmological equivalent of a flat canvas. But how could this possibly work? Think of a hologram you might see on a credit card. Shine light on it, and a three-dimensional image appears, even though the data is stored on a flat, two-dimensional surface. The holographic principle suggests space-time operates similarly. The pixels of our reality, the smallest units of information, could reside on the universe's outer edge, with our experiences unfolding as a kind of cosmic projection. Even time itself might be part of this illusion, emerging from the way that underlying data interacts. If this sounds mind-bending, consider the implications. The holographic principle could solve one of physics' most vexing paradoxes: how to reconcile quantum mechanics, which governs the very small, with general relativity, which describes the very large. In this framework, gravity might not be a fundamental force at all, but a side effect of how information is processed on that deeper, two-dimensional layer. It's as if the universe runs on a kind of quantum code, with the laws of physics acting like software glitches in a vast computational system. Supporters of the idea point to tantalizing clues. The cosmic microwave background, the afterglow of the Big Bang, shows patterns that some physicists argue resemble the pixelation you'd expect from a holographic universe. Others note that the principle naturally limits the amount of information in any region of space, preventing the nonsensical infinities that plague other theories. Even more intriguingly, it suggests that chaos and order might not be opposites, but different expressions of the same underlying data. The randomness of quantum fluctuations, the structure of galaxies, all could be facets of a single, unified holographic process. Yet skeptics remain. Without direct experimental proof, the holographic principle risks being labeled as metaphysics rather than physics. Detecting its signatures would require technology far beyond our current reach, perhaps an instrument sensitive enough to measure the graininess of space-time itself. But the search is on. Experiments using ultra-precise lasers and gravitational wave detectors might one day reveal whether space is smooth or pixelated, just as a high-resolution screen exposes the dots in an image. Whether the holographic principle holds up or not, it forces us to confront a profound question. What is reality, if not what we see and touch? If the universe is indeed a projection, then the chaos that birthed galaxies and the order that sustains them might both be part of something far deeper, a hidden layer where information, not matter, is the true currency of existence. And that realization could rewrite not just cosmology, but our very understanding of what it means to be real. One of the most perplexing contradictions in cosmology is how our universe seems to defy its own fundamental rules. The second law of thermodynamics tells us that entropy, a measure of disorder, must always increase over time. Left to its own devices, any system will tend toward chaos, like a sandcastle crumbling into the sea or a drop of ink dispersing in water. Yet here we are, surrounded by galaxies, planets, and life structures of breathtaking complexity that emerged from a featureless sea of primordial energy. How can a universe governed by entropy produce such intricate order? The answer lies in a cosmic tug of war between two opposing forces, the relentless drive toward disorder and the peculiar organizing power of gravity. Picture the early universe as a perfectly smooth, ultra-hot soup of particles. By the strictest definition, this was actually a low entropy state, strange as that sounds. Because all that energy was distributed so uniformly, there were no temperature differences, no clumps of matter, no pockets of greater or lesser disorder. But as the universe expanded and cooled, gravity began sculpting the first imperfections. Tiny quantum fluctuations, stretched across the cosmos during inflation, became the seeds for matter to gather. And here's where gravity plays its surprising role. While entropy pushes systems toward disorder, gravity does the opposite on large scales. It pulls matter together, creating dense clusters where entropy locally decreases, even as the overall disorder of the universe continues to rise. Think of it like a bustling city springing up in the middle of a desert. The city represents a pocket of concentrated order: buildings, roads, electricity, while the surrounding wilderness grows ever more chaotic. The city doesn't violate the laws of thermodynamics. It simply exports its entropy outward. In the same way, stars and galaxies are like cosmic cities, drawing in matter and energy to create islands of structure, while the vast voids between them become increasingly disordered. This delicate balance is why we can exist at all. Without gravity's counterintuitive effect, the universe would have remained a thin, uniform haze: no stars, no planets, just an eternal drift toward maximum entropy. But this raises an even deeper question. Why was the early universe in such a low entropy state to begin with? Some physicists argue this is the real mystery at the heart of cosmology. A universe starting in total equilibrium, maximum entropy, would have no arrow of time, no driving force for change. The fact that we perceive time moving forward at all might be a direct consequence of that initial low entropy condition. One provocative theory suggests that our universe's orderly beginning could be linked to the multiverse. If countless universes exist, each with random initial conditions, ours might simply be one where the improbable happened, a fleeting fluctuation in an otherwise chaotic multiverse, destined to eventually return to disorder. Yet despite entropy's inevitable victory in the far future, we live in a golden age of cosmic structure. For billions of years, gravity has worked against the tide of disorder, weaving galaxies and igniting stars. Life itself may be another example of local entropy defiance, a temporary eddy in the great current of cosmic decay. It's a humbling thought. The very laws that push the universe toward chaos also, paradoxically, make complexity possible. And that tension between gravity's pull and entropy's push is what transformed a formless fireball into the rich tapestry we see today. The universe runs on numbers constants so precise, even a slight tweak would render existence impossible. Take gravity, for instance. If it were just a fraction stronger, stars would burn out too quickly for planets to form, a hair weaker, and matter would never have clumped into galaxies at all. Or consider the cosmological constant, which governs the universe's expansion rate. Adjust it by 1 part in 100 million, and you'd either get a runaway collapse or a cosmos so sparse, no structures could ever emerge. These aren't hypotheticals, they're mathematical certainties. The universe's ability to host life hinges on a razor-thin balance of forces, as if someone dialed in the perfect settings. This fine-tuning problem has sparked fierce debate. Some scientists argue it's simply a cosmic coincidence, that we're here because statistically, some universe had to hit the jackpot. Others propose the multiverse as a solution. If infinite universes exist with random parameters, ours is just the lucky one where everything aligned. But there's a third, more provocative possibility, that these constants aren't arbitrary at all. Could they be the inevitable outcome of a deeper, undiscovered law? String theory, for example, suggests these constants might be fixed by the geometry of hidden dimensions, like notes dictated by the shape of an instrument. Yet the fine-tuning problem also brushes against philosophy. Does the universe's apparent design imply a designer, or is that an illusion born of our limited perspective? Think of a puddle marveling at how perfectly its hole fits its shape. Our very existence might bias us toward seeing purpose where there's only chance. But here's the twist: science keeps uncovering layers of fine-tuning within fine-tuning. The strong nuclear force, for instance, is calibrated so precisely that carbon, the backbone of life, can form in stars. Even the ratio of protons to electrons is balanced to allow chemistry as we know it. The stakes couldn't be higher. If these constants were truly random, life would be a freak accident in a hostile cosmos. But if they're inevitable, we might be on the verge of a paradigm shift, a theory that explains why the universe had to be this way. Until then, the fine-tuning problem remains one of science's most tantalizing loose ends, a riddle written into the fabric of reality itself. Whether it points to multiverses, deeper physics, or something beyond, one thing is clear: our universe's recipe is far more delicate and mysterious than we ever imagined. Stretching across the entire sky like a silent whisper from the dawn of time, the cosmic microwave background is the oldest light we can see, a fading echo of the universe's fiery birth. Imagine catching a photograph of yourself as a newborn, but this one was taken when the cosmos was just 380,000 years old, a mere infant in cosmic terms. Back then, the universe had cooled enough for protons and electrons to combine into hydrogen atoms, transforming the opaque plasma into transparent space and releasing a burst of radiation that's been traveling ever since. Today, that light has stretched into microwaves, invisible to our eyes but detectable with sensitive telescopes, painting a ghostly map of the early universe's structure. What makes this glow so remarkable isn't just its age, it's the story written in its subtle imperfections. To the naked eye, the CMB appears nearly uniform, varying by less than 1 part in 100,000. But those tiny fluctuations, those faint hotter and cooler spots, are the universe's original blueprints. They're the gravitational seeds planted during inflation, microscopic quantum ripples magnified to cosmic scales, destined to become the galaxies and voids we see today. It's as if we're staring at the faint fingerprints of the cosmos's creator, preserved in the cold stillness of space. Scientists decode these patterns like astronomers reading a celestial Rosetta Stone. The hotter regions mark where matter was slightly denser, places where gravity would later pull in more gas and dust, forging the first stars. The cooler patches became the vast cosmic deserts between galaxy clusters. By measuring the exact size and distribution of these fluctuations, researchers can test theories about the universe's composition. How much is dark matter? How much is dark energy? Even the geometry of space-time itself. The CMB has confirmed with stunning precision that our universe is flat, expanding, and dominated by invisible forces we're only beginning to understand. But the CMB isn't just a relic, it's a time machine. In 2013, the Planck satellite delivered the most detailed map ever, revealing anomalies that still puzzle cosmologists. Why is one half of the sky slightly cooler than the other? Could this be evidence of a pre-Big Bang universe, or just a statistical fluke? Some speculate these irregularities hint at a larger cosmic structure beyond our observable horizon, while others wonder if they challenge inflation itself. The CMB's mysteries remind us that every answer uncovers new questions, and the universe's first light still has secrets to share. What's truly humbling is realizing we're made of the same stuff as those ancient temperature variations. The carbon in your bones, the iron in your blood, all forged from atoms that once traced those slight density variations in the primordial plasma. The CMB isn't just a distant echo, it's the mirror showing us our own cosmic reflection, a reminder that we're not just observers of the universe, but active participants in its unfolding story. And as telescopes grow more advanced, who knows what other whispers from the dawn of time we might yet decipher? For hundreds of thousands of years after the Big Bang, the universe remained a searing, opaque fog, a roiling plasma so hot that electrons couldn't latch onto atomic nuclei. Light particles, or photons, were trapped in this chaotic dance, constantly scattering off free electrons like pinballs in a cosmic arcade. Then, around 380,000 years after the beginning, something extraordinary happened. The expanding cosmos finally cooled below 3,000 degrees, about the temperature of a candle flame, and in that critical moment, the universe became transparent for the first time. This was the era of recombination, when protons and electrons slowed enough to form the first stable hydrogen atoms. Picture it like a cosmic game of musical chairs. As the music of extreme heat faded, charged particles finally found their partners, leaving photons free to travel unimpeded across space. That sudden liberation of light is what we now detect as the cosmic microwave background, the afterglow of creation itself. But recombination wasn't just about light breaking free. It marked the universe's transition from chaos to structure. With neutral atoms now dominating, gravity could begin its slow, patient work, pulling matter into denser regions that would eventually ignite as the first stars. Here's the astonishing part. If recombination had happened even slightly differently, our cosmos might look utterly alien. Had the universe cooled faster, atoms might have formed too early, creating denser clumps that collapsed into black holes instead of stars. Slower, and the plasma might have remained too diffuse, preventing galaxies from ever taking shape. The timing was so precise, it's as if the cosmos knew exactly when to switch phases, like a master chef pulling a soufflé from the oven at the perfect moment. Yet this pivotal era also left behind subtle clues about the universe's infancy. The CMB's temperature variations, those faint hotter and cooler spots, reflect the density differences in the primordial plasma. Where matter was slightly more concentrated, photons had to climb out of stronger gravitational wells, losing energy and appearing cooler. These minute fluctuations became the architectural blueprints for everything to come, frozen in time like cosmic fossils. Without them, the universe would have remained featureless, a vast, empty expanse with no galaxies, no stars, and no planets. What's even more remarkable is how fragile this process was. Hydrogen atoms, once formed, were just one high-energy photon away from being ripped apart again. It took another 100 million years, a period called the Cosmic Dark Ages, before the universe cooled enough to make these bonds permanent. Only then could the stage be set for the next act, the dawn of starlight, when gravity's patience finally paid off and the cosmos ignited its first beacons in the darkness. So when we look at the CMB, we're not just seeing light from the distant past. We're witnessing the universe's first breath of clarity, the moment it emerged from chaos and took its first step toward the ordered cosmos we call home. And every atom in your body, every star in the sky, traces its existence back to that delicate, fleeting instant when the cosmos finally became transparent. After the cosmic dark ages, that vast stretch of time when the universe was a silent, starless expanse, something extraordinary began to stir. The first stars weren't like the ones we know today. Born from pristine clouds of hydrogen and helium, these pioneers were monsters, dozens or even hundreds of times more massive than our sun. And when they ignited, their searing ultraviolet light acted like a cosmic blowtorch, tearing electrons from neutral hydrogen atoms and flooding the universe with radiation once again. This was the Epoch of Reionization, the universe's second great transformation, when the fog lifted for good and light finally regained dominion over darkness. Imagine the scene, islands of brilliance flickering to life in an endless sea of black. These first galaxies, small and fragile by today's standards, were the matchsticks that set the cosmos ablaze. Their radiation carved vast, transparent bubbles in the hydrogen fog, like melting holes in ice. Over hundreds of millions of years, these bubbles grew and merged until the entire universe became ionized once more, not from heat, as in the Big Bang's aftermath, but from starlight. It was a slow, uneven process, with some regions reionizing early while others lingered in shadow. Even today, astronomers detect whispers of this era in the faint glow of distant quasars, whose light bears the telltale fingerprints of the last stubborn patches of neutral hydrogen. But why did this happen? The answer lies in the delicate balance between light and matter. Those first stars were so massive, they burned ferociously and died young, exploding as supernova that seeded the cosmos with heavier elements. Their intense radiation was powerful enough to strip electrons from atoms, but it also sealed their own fate. By ionizing their surroundings, they created a feedback loop. Clearing the fog allowed light to travel farther, which in turn triggered more star formation in distant regions. It was a cosmic domino effect, with each generation of stars pushing the boundaries of transparency further into the void. The echoes of reionization are still with us. When astronomers peer at the most distant galaxies, those whose light has traveled over 13 billion years to reach us, they are essentially looking back in time to this pivotal era. Some of these ancient galaxies appear surrounded by vast hydrogen bubbles, like lighthouses piercing a receding mist. Others show signs of violent quasar activity, their central black holes spewing radiation that accelerated reionization in their neighborhoods. Together, these observations paint a picture of a universe in flux, where light and matter waged a slow-motion battle for supremacy. What's truly astonishing is how fragile this process was. Had those first stars been slightly less massive, their light might not have been strong enough to ionize hydrogen on a cosmic scale. Without reionization, the universe might have remained forever opaque, its galaxies hidden behind an impenetrable veil. Instead, the cosmos crossed a threshold, clearing the way for light to travel freely across billions of years. Light that now carries the stories of quasars, supernova, and the birth of galaxies to our telescopes. We owe our view of the universe to those first brilliant sparks that set the darkness aflame. The universe's first stars didn't just light up the cosmic dark ages, they transformed the very fabric of reality. Known as Population 3 stars, these celestial titans were unlike anything we see today. Born from clouds of pure hydrogen and helium, uncontaminated by heavier elements, they burned at temperatures that would make modern stars look like candles. With masses up to 300 times that of our Sun, they lived fast and died young, their brilliant but brief lives lasting just a few million years before exploding in cataclysmic supernova that would change the cosmos forever. What made these stars so special wasn't just their size, it was their role as the universe's first alchemists. In their cores, nuclear fusion forged the first traces of carbon, oxygen, and other elements essential for life. When they exploded, they scattered these precious materials across space like cosmic gardeners planting seeds for future worlds. Without these violent deaths, there would be no rocky planets, no water, no chemistry complex enough to give rise to life. Every element in your body heavier than hydrogen and helium was once forged in the heart of a long-dead Population 3 star. Yet for all their importance, these stellar pioneers remain frustratingly elusive. No telescope has ever directly observed one. The reason? They burned out so quickly that by the time their light could reach us across billions of years, they'd already vanished. But astronomers aren't giving up. Cutting-edge instruments like the James Webb Space Telescope are searching for their faint fingerprints, peculiar chemical signatures in ancient gas clouds, or unusual patterns in the light from the most distant galaxies. Some scientists even hope to catch the last, dying embers of a population 3-star in the act of exploding, a flash of ultraviolet light that could travel across time to reach our detectors. The hunt isn't just about solving a cosmic mystery, it's about understanding our own origins. These stars weren't just the first lights in the universe, they were the architects of everything that followed. Their explosions triggered shock waves that compressed nearby gas, birthing second-generation stars in greater numbers. Their heavy elements became the raw materials for planets. And their intense radiation helped ionize the universe, clearing the fog of neutral hydrogen that had blanketed space since the Big Bang. In a very real sense, we owe our existence to these long-vanished giants. One of the most tantalizing theories suggests that some population 3 stars might still exist today, not as shining beacons, but as dark, dead remnants. If the very first stars were massive enough, they wouldn't have exploded as supernova at all. Instead, they might have collapsed directly into black holes, invisible sentinels from the dawn of time that could still be lurking in our galactic neighborhood. Finding one would be like discovering a living fossil, a relic from the universe's fiery infancy. As technology pushes the boundaries of what we can observe, each new telescope brings us closer to glimpsing these cosmic pioneers. And when we finally do, it won't just fill a gap in our knowledge, it will connect us directly to the moment when chaos first gave way to structure, when the featureless early universe took its first steps toward becoming the rich, complex cosmos we call home. The story of the first stars isn't just astrophysics, it's the origin story of everything. Black holes aren't just cosmic vacuum cleaners, they're master sculptors, shaping the universe on scales we're only beginning to understand. At the heart of nearly every galaxy, including our own Milky Way, lurks a supermassive black hole, millions to billions of times heavier than our Sun. But these aren't passive monsters simply devouring everything nearby. Their gravitational influence reaches far beyond their event horizons, acting like cosmic puppeteers that can accelerate, disrupt, or even shut down star formation across entire galaxies. Take the relationship between a black hole's growth and its host galaxy. For decades, astronomers noticed something peculiar. The more massive the galaxy, the larger its central black hole. This wasn't mere coincidence. As black holes feast on surrounding gas and dust, they unleash torrents of energy in the form of quasars, beacons so bright they can outshine all the stars in their galaxy combined. These outbursts heat up nearby gas, preventing it from cooling and collapsing into new stars. It's a self-regulating system. Too much star formation feeds the black hole, which then suppresses further star birth with its intense radiation. Without this balancing act, galaxies might either burn through their fuel too quickly or never form stars efficiently at all. But here's where it gets even more fascinating. Black holes might not just be residents of galaxies, they could have been their architects. Some theories suggest that in the early universe, dark matter halos, the invisible scaffolding of cosmic structure, collapsed first, creating dense pockets where primordial gas could accumulate. At the centers of these knots, direct collapse black holes may have formed, seeding the birth of galaxies around them. Imagine a tiny black hole acting like a gravitational anchor, pulling in streams of gas that eventually ignited as the galaxy's first stars. Over billions of years, both the galaxy and its central black hole grew in tandem, locked in a dance of mutual creation. Evidence for this comes from quasars detected in the distant universe, active black holes shining brilliantly when the cosmos was less than 1 billion years old. These objects couldn't have formed through normal stellar processes. There simply wasn't enough time. Instead, they likely grew from massive seeds born in the chaotic early universe, where vast clouds of gas collapsed directly into black holes without ever forming stars. These primordial behemoths then guided the assembly of the first galaxies around them, turning random fluctuations into organized structures. Yet black holes don't just build, they also destroy. When two galaxies collide, their central black holes eventually spiral together, merging in a cataclysmic event that shakes spacetime itself. The gravitational waves from such mergers ripple across the cosmos, carrying energy equivalent to millions of supernovae. These violent encounters can fling stars out of their galaxies or trigger new bursts of star formation, remixing the cosmic ingredients in unpredictable ways. It's a reminder that creation and destruction are two sides of the same coin. The chaos that birthed black holes also gave them the power to impose order. What's truly humbling is realizing that without these gravitational powerhouses, the universe might look entirely different. Too many black holes and galaxies would be stripped of their star-forming gas too soon. Too few, and the cosmic web might lack the anchors needed to organize matter efficiently. Like Goldilocks porridge, the balance had to be just right, and somehow, against astronomical odds, it was. The next time you gaze at the Milky Way's shimmering band, remember, its spiral arms, its bustling stellar nurseries, even its tranquil outskirts all bear the subtle imprint of the dark giant silently reigning at its heart. The universe isn't just a random scattering of galaxies, it's an intricate cosmic tapestry, woven together by gravity over billions of years. Picture an unimaginably vast spiderweb, stretching across billions of light years, with galaxies strung like glittering beads along its silken threads. This is the cosmic web, the largest structure in existence, where thin filaments of dark matter and gas intersect at dense nodes, leaving behind enormous, empty voids so vast they could swallow thousands of galaxies whole. And what's truly remarkable is how this delicate architecture emerged from near-perfect uniformity, a transformation so gradual, it makes the formation of mountain ranges look instantaneous. The story begins with those faint quantum ripples from the early universe, the same ones imprinted in the cosmic microwave background. Over time, gravity got to work, tugging ever so slightly harder on regions where matter was marginally denser. Like a snowball rolling downhill, these pockets grew, pulling in more gas and dark matter, while the emptier regions stretched into cavernous gaps. The dark matter, invisible and mysterious, formed the skeleton of this web, its gravity guiding ordinary matter into place. Gas flowed along these hidden channels, pooling at the intersections where galaxies would eventually ignite. It's as if the universe was following an invisible blueprint, one drawn by the faintest whispers of imbalance from the Big Bang. Today, astronomers map this web by observing the positions of millions of galaxies, revealing a structure so vast it defies human intuition. The filaments themselves are barely visible threads of hot gas glowing faintly in X-rays, but their influence is everywhere. Galaxy clusters, the universe's largest gravitationally bound structures, sit at the web's busiest intersections, while isolated galaxies drift along the quieter strands. And between them, the void's regions so empty, a single galaxy might be the only resident for hundreds of millions of light years. These cosmic deserts aren't just gaps, they're active players, their emptiness shaping the way galaxies move and clusters merge. What's astonishing is how much this structure tells us about the universe's hidden ingredients. The web's pattern, the spacing of its filaments, the sizes of its voids acts like a cosmic barcode, encoding secrets about dark matter's nature and dark energy's push. Simulations show that without dark matter's gravitational glue, the web would lack its fine, thread-like structure. Without dark energy's accelerating expansion, the voids wouldn't stretch as dramatically as they do. Even the distribution of galaxies along the filaments hints at the universe's expansion history, like growth rings in a tree, yet mysteries remain. Why do some filaments seem to stretch farther than physics predicts? Could there be larger patterns beyond what we've mapped? Some theories suggest the cosmic web might even connect to other, unseen universes in a sprawling multiverse, though that's still speculative. What's certain is that this web isn't static. It's a dynamic, evolving entity with galaxies sliding along filaments like beads on a string, pulled toward the densest clusters in a slow-motion dance that will continue for billions of years. So the next time you see an image of the cosmic web, remember, you're not just looking at a map of the universe. You're seeing the end result of a transformation that began with quantum flickers smaller than atoms, a structure so grand it makes galaxies seem like mere specks of dust on its threads. And somewhere in that web, on an unremarkable filament in an ordinary cluster, our Milky Way spins quietly, a single stitch in the universe's infinite embroidery. Billionths of a second after the Big Bang, the universe wasn't just hot and dense, it was loud, a roiling sea of plasma, packed with protons, electrons, and photons, vibrated with pressure waves that raced outward at half the speed of light. These weren't ordinary sound waves, they were cosmic tsunamis, compressing matter into dense shells with each pulse, like ripples freezing in place as the universe cooled. Today, we can still see their echoes etched into the cosmos, a fossilized rhythm that reveals the universe's expansion history with breathtaking precision. These frozen ripples, known as Baryon acoustic oscillations, act like a cosmic ruler etched into the fabric of space. Imagine dropping a pebble into a pond and watching the circular waves expand. Now picture that same process happening in the primordial universe, but instead of water, the waves moved through a superheated plasma. When the universe cooled enough for atoms to form, those waves froze mid-ripple, leaving behind spherical shells of matter over dense regions where galaxies would later cluster. The result, a subtle but unmistakable pattern. Pairs of galaxies are slightly more likely to be separated by about 500 million light-years, the distance those sound waves traveled before freezing. What makes this so valuable to astronomers is that this distance, this standard ruler, stays constant over cosmic time. By measuring how much this scale appears stretched or compressed in different eras, we can track how the universe's expansion has accelerated or slowed. It's like finding a ruler that magically adjusts its markings to reveal how space itself has stretched. When combined with other cosmic yardsticks, like supernova or the cosmic microwave background, Baryon acoustic oscillations become one of our most powerful tools for measuring dark energy's grip on the cosmos. The story gets even richer when we consider why these oscillations exist at all. In the early universe, photons and baryons, ordinary matter, were locked in a tug of war. Photons exerted outward pressure while gravity pulled matter inward. This created oscillations with matter compressing and rarefying in waves. When the universe cooled enough for atoms to form, photons decoupled from matter, leaving those density variations imprinted like footprints in cosmic cement. Over billions of years, gravity amplified these footprints, sculpting the web of galaxies we see today. Yet these oscillations aren't just relics, they're active players in cosmology. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies to reveal this faint pattern, a whisper from the universe's infancy that helps us test theories of gravity, dark matter, and dark energy. Some models even suggest slight deviations from the expected scale could hint at new physics, are perhaps evidence of exotic dark energy behavior or extra dimensions. So the next time you see a map of galaxy clusters, remember, you're not just looking at points of light, you're witnessing the aftermath of a primordial symphony, a rhythm set in motion when the universe was a seething, screaming plasma, now frozen in time as the cosmos's most enduring metronome. And with every new galaxy survey, we're tuning into that ancient frequency, listening for clues to the universe's past and its ultimate fate. Among all the particles that flooded the early universe, none are quite as elusive or as influential as the neutrino. Born in the first seconds after the Big Bang, these ghostly particles outnumber atoms by billions to one, yet they slip through entire planets as if they weren't there. With no electric charge and almost no mass, neutrinos rarely interact with matter, making them cosmic phantoms that physicists have spent decades trying to catch. But don't let their shyness fool you. These tiny particles may have played an outsized role in sculpting the universe we see today. Picture the cosmos just 1 second old, a seething cauldron of energy so dense that light couldn't travel more than a fraction of an inch before colliding with something. In this primordial soup, neutrinos were born in staggering numbers, flooding space with an invisible tide. Even today, trillions pass through your body every second, remnants of that explosive beginning. What makes them extraordinary isn't just their abundance, it's their subtle gravitational influence. While a single neutrino's pull is negligible, their collective gravity, spread across the entire universe, might have gently nudged matter into the first clumps that would become galaxies. Scientists suspect these particles left fingerprints on the cosmic microwave background, those faint temperature variations that became the universe's blueprint. Neutrinos, moving at nearly the speed of light, would have smoothed out some of the smaller density fluctuations while leaving larger ones intact. The result? A subtle but measurable shift in how galaxies cluster today, slightly fewer small galaxy groups and more large-scale structures than there would have been without neutrinos' smoothing effect. It's as if an invisible hand brushed across the cosmos in its infancy, subtly editing the distribution of matter. The hunt for these primordial neutrinos is one of physics' greatest challenges. Modern detectors like IceCube buried deep in Antarctic ice or Super Kamiok and a tank of ultra-pure water beneath a Japanese mountain catch fleeting interactions when a neutrino, against all odds, collides with an atom. But these detectors spot neutrinos from recent cosmic events like supernova or the Sun. The oldest neutrinos, those from the Big Bang itself, have cooled to near absolute zero over 13 billion years, their energy so feeble that current technology can't definitively trap them. Yet the payoff for catching them would be immense. Primordial neutrinos could reveal secrets about the universe's first moments that even light can't tell us. Unlike photons, which scattered endlessly in the early plasma, neutrinos decoupled from matter just 1 second after the Big Bang, carrying an undisturbed snapshot of that chaotic era. Studying them could help answer why matter dominates over antimatter, or even uncover hidden forces that shaped the cosmos before atoms formed. What's truly humbling is realizing how much of the universe's story might be written in particles we can barely detect. Neutrinos remind us that the cosmos isn't just built from what we can see. It's shaped by the invisible, the subtle, and the nearly forgotten. And as we push the boundaries of detection, we might yet find that these spectral messengers hold the keys to understanding how chaos first gave way to order. Supersymmetry is one of the most beautiful ideas in physics, a theory so elegant it promised to solve multiple cosmic puzzles at once. The concept is deceptively simple. Every particle we know, from quarks to photons, should have a hidden twin, a heavier superpartner with slightly different properties. Electrons would have selectrons, quarks would have squarks, and even the force-carrying particles like gluons would have their own mysterious counterparts called gluinos. These superpartners wouldn't just be theoretical curiosities. They could be the key to unlocking dark matter's identity, unifying the fundamental forces, and even explaining why the Higgs boson has the mass it does. At first glance, supersymmetry seems almost too good to be true. It elegantly patches gaps in the standard model of particle physics, which, for all its successes, can't explain gravity's weakness compared to other forces, or why the universe contains so much invisible matter. If supersymmetry were real, the lightest superpartner, often called the neutralino, would be stable, electrically neutral, and nearly invisible, ticking all the boxes for a dark matter candidate. The theory also offers a breathtaking symmetry between matter and force-carrying particles, something physicists have long suspected must exist at deeper levels of reality. Yet after decades of searching, from underground detectors to the Large Hadron Collider, not a single superpartner has shown up. Particle accelerators have smashed protons together at energies that should have revealed these hidden twins, while sensitive experiments hunting for dark matter's faint signals have come up empty-handed. It's as if nature is teasing us with a solution just out of reach, dangling the promise of order while withholding the proof. This absence has left physicists at a crossroads. Some argue we simply haven't looked hard enough, that superpartners might be far heavier than originally predicted, hiding just beyond our current technological grasp. Others suggest supersymmetry might manifest in ways we haven't anticipated, with particles that decay too quickly to detect or properties that evade conventional searches. A more radical possibility is that the theory, while mathematically stunning, might not describe our universe at all. What makes this uncertainty so fascinating is how it reflects the scientific process at its most raw. Supersymmetry isn't just a theory, it's a bet on nature's underlying harmony, a wager that the universe prefers elegant solutions over messy ones. Whether that bet pays off or not, the search has already pushed technology to new heights, from ultra-sensitive detectors to colliders of unprecedented power. And if superpartners do eventually appear, they wouldn't just fill a gap in our equations, they'd open a portal to a hidden layer of reality, one where every particle we know is just half of a much grander story. For now, supersymmetry remains in limbo, a ghost at the edges of physics. But its very possibility reminds us how much we still don't understand, and how the universe's greatest secrets might be waiting in the spaces between what we can see and what we can only imagine. The idea of a universe that endlessly dies and reboots itself sounds like something from ancient mythology, yet it's a serious scientific proposition. The cyclic universe model suggests that rather than a single explosive beginning, our cosmos might be trapped in an infinite loop of expansion and collapse, each cycle starting with a big bang and ending in a big crunch. Picture a cosmic heartbeat where space itself breathes in and out over trillions of years, with every collapse seeding the next explosive rebirth. In this view, the order we see today, galaxies, stars, planets, isn't permanent. It's just a fleeting phase in an eternal dance between chaos and structure. What's fascinating is how this theory tackles some of cosmology's biggest puzzles. If the universe cycles endlessly, there's no need for a mysterious beginning or a definitive end. The fine-tuning of physical constants, which seems so improbable in a one-time universe, could be the result of trial and error across countless cycles. Each reset might slightly tweak the rules, with only the cycles that produce stable structures like galaxies surviving long enough to spawn the next iteration. It's a Darwinian take on cosmology, where the laws of physics themselves evolve over cosmic time. But how could such a cycle even work? One version of the theory relies on dark energy, the same force accelerating the universe's expansion today, eventually weakening or reversing its effect. Imagine dark energy as a stretched spring. After pushing galaxies apart for billions of years, it might lose tension, allowing gravity to pull everything back together. As matter and energy compress toward a single point, quantum effects could trigger a rebound, igniting a new Big Bang from the ashes of the old universe. The process wouldn't be identical each time. Tiny differences in each cycle could explain why our universe looks the way it does, while others in the sequence might have been wildly different. Supporters of cyclic models point to intriguing clues. The cosmic microwave background shows anomalies, unexpected cold spots, and asymmetries that some interpret as bruises from a pre-Big Bang collision between universes in a larger multiverse. Others note that certain string theory models naturally lead to cyclic behavior, with hidden extra dimensions collapsing and re-inflating in ways that reset our visible universe. Even the mysterious nature of dark energy, which seems fine-tuned to allow structure formation, could make sense if it's a recurring phase in a grander cycle. Yet the theory faces formidable challenges. Current observations suggest the universe's expansion is accelerating, not slowing down as a future big crunch would require. Unless dark energy's behavior changes dramatically, everything may drift apart forever, leaving no possibility of a cyclical reboot. There's also the problem of entropy. The universe's disorder increases with each cycle, making it unclear how order could regenerate indefinitely without violating thermodynamics. Some physicists propose that entropy resets during the Big Crunch, though the mechanism remains speculative. What's compelling about the cyclic model isn't just its audacity, it's how it reframes our place in cosmic history. If true, the galaxies we see might be echoes of countless previous universes, their structures imprinted with faint memories of earlier cycles. The atoms in your body could have been forged in a Big Bang that happened before time as we know it began. And the universe's apparent order wouldn't be a one-time miracle, but the latest iteration of an eternal pattern where chaos and structure take turns shaping reality. Whether the cycles are real or not, the idea stretches our imagination beyond a single cosmic story. It hints at a universe far older and more resilient than we've dared to conceive, one where endings are just beginnings in disguise, and where the fragile balance we call home might be just one verse in an infinite cosmic poem. What if the universe's greatest mystery isn't a missing substance, but a fundamental misunderstanding of gravity itself? That's the radical proposition behind emergent gravity, a theory that dares to suggest dark matter might not exist at all. Instead, the strange behavior of galaxies, their unexplained rotation speeds, the way they bend light, could stem from gravity working differently on cosmic scales than our current equations predict. Imagine discovering that the force keeping your feet on the ground transforms into something entirely new when applied to the vast emptiness between galaxies. This isn't science fiction, it's a serious challenge to cosmology's status quo, one that could upend decades of research with a single elegant twist. The idea first gained traction when physicist Eric Verland proposed that gravity might not be a fundamental force at all, but rather an emergent phenomenon, a side effect of deeper quantum-level interactions, much like temperature emerges from the motion of atoms. In this view, the fabric of spacetime itself contains hidden information, and gravity arises from how that information gets rearranged as matter moves through it. On Earth's surface or within our solar system, this subtle effect aligns neatly with Newton and Einstein's predictions. But in the near-empty voids between galaxies, where dark matter's influence is most apparent, emergent gravity suggests space's underlying structure generates extra attraction, no invisible particles required. Critically, this theory reproduces dark matter's effects without invoking any unseen substance. Spiral galaxies' rotation curves, which famously defy Newtonian physics unless you add dark matter's gravitational pull, naturally match emergent gravity's predictions. Even the bending of light around galaxy clusters, usually explained by dark matter's extra mass, fits the model. It's as if we've spent decades searching for a hidden actor in a play, only to realize the stage itself was responsible for all the mysterious movements. Yet emergent gravity isn't without hurdles. While it explains certain galactic behaviors, it struggles with other observations, like the bullet cluster, a cosmic collision where visible matter and gravitational effects appear separated, as if dark matter got left behind. Proponents argue emergent gravity might still account for this with modifications, but skeptics see it as a fatal flaw. Meanwhile, alternative theories like modified Newtonian dynamics, which also tweak gravity's rules, have faced similar challenges when tested against the full range of cosmic data. What makes emergent gravity compelling isn't just its potential to simplify cosmology, it's how deeply it reimagines reality. If gravity emerges from quantum information, then space-time itself might be a kind of hologram, its properties woven from microscopic bits we can't yet perceive. This bridges two of physics' greatest puzzles, the nature of gravity and the search for quantum gravity. Suddenly, the quest to unify general relativity and quantum mechanics looks less like stitching two mismatched fabrics and more like peeling back layers of a single, deeper truth. The debate is far from settled. Traditional dark matter models, bolstered by precise measurements of the cosmic microwave background and large-scale structure, still hold the mainstream. But science thrives on such challenges, the moments when someone dares to ask if we've been walking in circles around an answer that demands a leap instead. Whether emergent gravity ultimately succeeds or fails, it reminds us that the universe's greatest secrets might not lie in what we've missed, but in what we've assumed too firmly to question. And that's how revolutions begin. Black holes aren't just cosmic vacuum cleaners, they're information shredders, or so it once seemed. According to Einstein's general relativity, anything crossing a black hole's event horizon is lost forever, crushed into a singularity where space and time cease to have meaning. But quantum mechanics, the rulebook governing the subatomic world, insists that information can never truly be destroyed. It might get scrambled beyond recognition, but in principle, it should always be recoverable. This clash between two foundational theories, general relativity's merciless annihilation and quantum mechanics' ironclad preservation, is the infamous black hole information paradox, a puzzle so profound its solution could rewrite our understanding of reality. Enter the firewall hypothesis, one of the most startling proposals to resolve this paradox. Imagine approaching a black hole, expecting the smooth, uneventful descent predicted by relativity, only to hit a searing wall of high-energy particles just inside the event horizon. This firewall would incinerate anything crossing it, preserving information by encoding it in the radiation, but violently contradicting Einstein's vision of free fall. The idea emerged from a thought experiment. If quantum mechanics ensures information escapes via Hawking radiation, then the radiation near the horizon must be entangled with particles both inside and outside the black hole. But quantum rules forbid such monogamous entanglement from being shared in multiple places. The firewall acts as a cosmic reset, severing old entanglements to make room for new ones, but at a horrific cost, turning black holes from gentle traps into cosmic kill zones. Yet firewalls aren't the only solution. The holographic principle offers a subtler, more elegant way out. If the universe truly behaves like a hologram, with all information encoded on a two-dimensional surface, then black holes might simply project their contents onto their event horizons like cosmic projectors. Instead of information being lost inside, it's smeared across the boundary in quantum bits, preserved but scrambled into a form we can't yet decipher. This would mean the chaos we associate with black holes isn't destruction, it's transformation, like burning a book but preserving its ashes in a way that, in theory, could reconstruct every page. The stakes couldn't be higher. If information is truly preserved, even in black holes, it suggests a deep unity between gravity and quantum mechanics, a hint that space-time itself might emerge from something more fundamental. But if firewalls are real, our understanding of relativity collapses at the horizon, revealing a universe far more violent and unpredictable than we imagined. Either way, the paradox forces us to confront the limits of our theories, pushing physics toward a revolution as profound as relativity or quantum mechanics was in their time. What's fascinating is how this debate mirrors the universe's own dance between chaos and order. Black holes, the ultimate symbols of cosmic destruction, might also be the keys to understanding how information, the bedrock of reality, persists against all odds. And as physicists grapple with these ideas, they're not just solving a puzzle, they're peering into the abyss, searching for the hidden rules that govern everything from the smallest particles to the largest structures in existence. The answer, when it comes, won't just tell us about black holes, it'll reveal how the universe stitches chaos into order, and how information, the universe's most resilient currency, survives even in the darkest corners of space. What if everything you know, the stars, the laws of physics, even your own thoughts, were nothing more than lines of code in an unfathomably advanced simulation? The simulation hypothesis suggests just that, proposing our universe might be an artificial construct, engineered by a civilization with technology so sophisticated, their creations wouldn't even recognize the boundaries of their own reality. It's a dizzying idea, one that takes ancient philosophical questions about existence and gives them a digital age twist. But here's the kicker. Some scientists argue this isn't just science fiction, it's a legitimate possibility worth considering. Think about how far human technology has come in just a few centuries. We've gone from abacuses to artificial intelligence, from stargazing to creating virtual worlds so immersive, they blur the line between the real and the rendered. If civilizations older than ours exist, their computational power might be beyond our wildest imagination. They could simulate entire universes, complete with conscious beings who believe their reality is as solid as we believe ours to be. In fact, if simulating universes is possible, the number of artificial realities could vastly outnumber the base reality, making it statistically more likely we're in one of the simulations. But how could we even test such a radical idea? Some physicists point to potential glitches, tiny anomalies in the fabric of reality that might hint at underlying code. For instance, if the universe were a simulation, it would likely run on discrete units of information like pixels in a video game. At extremely small scales, space and time might not be perfectly smooth but instead pixelated, a phenomenon some experiments have tried and failed to detect so far. Others suggest looking for computational shortcuts, like the universe rendering only what we observe, similar to how video games load graphics only when a player looks at them. Critics, of course, dismiss the hypothesis as untestable metaphysics. If a simulation were flawless, how could its inhabitants ever prove they're inside it? And if the creators didn't want us to know, they could simply erase any evidence, but supporters counter that the very laws of physics might contain clues. Take the speed of light, for example, a cosmic speed limit that seems arbitrary unless you consider it as a processing constraint, preventing the simulation from overloading. Even quantum mechanics' inherent uncertainty could reflect computational limits, like a system approximating outcomes rather than calculating every possibility. What's fascinating is how this idea reframes the universe's order. If we're in a simulation, the laws of physics aren't fundamental truths but programmed parameters, fine-tuned to produce a stable, interactive environment. The apparent fine-tuning of constant, like the strength of gravity or the mass of an electron, wouldn't be a cosmic coincidence but deliberate design choices. Chaos and order, in this view, might simply be different settings in a vast cosmic engine. Yet the simulation hypothesis isn't just about technology, it's about meaning. If reality is artificial, does that make our experiences less real? Or does it deepen the mystery, suggesting that consciousness itself might be a feature that transcends substrate, whether biological or digital? Ancient philosophers pondered whether we're shadows on a cave wall. Modern thinkers wonder if we're data in a server. The questions are eerily similar, even if the metaphors have evolved. Whether the universe is a simulation or not, the idea challenges us to rethink our place in the cosmos. It turns reality into a question rather than an assumption, inviting us to marvel not just at how the universe works, but at why it works the way it does. And in that sense, the hypothesis does something remarkable. It turns metaphysics into a scientific conversation, one where the boundaries between physics, philosophy, and imagination blur just like they might in a very, very good simulation. The universe seems suspiciously well suited for life, almost as if it knew we were coming. Consider the delicate balance required for our existence. If gravity were slightly stronger, stars would burn out too quickly. If the electromagnetic force were weaker, atoms couldn't form stable bonds. Even the cosmological constant, which governs the expansion of space, is fine-tuned to an astonishing precision. Alter it by a hair, and galaxies never coalesce. This uncanny alignment between the universe's laws and the requirements for life is the heart of the Anthropic Principle, an idea that bridges physics and philosophy in a way that's as provocative as it is profound. At its core, the Anthropic Principle suggests a simple but mind-bending truth. The universe must be compatible with conscious life because here we are observing it. It's like a cosmic version of the old tree falling and the forest question. If a universe existed with laws that prevented life, would anyone be there to notice? But this raises an even deeper question. Why does our universe have these life-friendly properties? One compelling answer comes from the multiverse theory. Imagine a vast cosmic lottery where countless universes bubble into existence, each with random physical constants. Most would be sterile, devoid of structure or observers. But a rare few, purely by chance, would hit the jackpot. Conditions just right for galaxies, planets, and eventually, beings capable of pondering their own existence. In this view, we're not special. We're just the inevitable inhabitants of one of the lucky universes where everything clicked. Yet not everyone finds this explanation satisfying. Some scientists argue it's a cop-out, a way to dodge the deeper mystery of why our universe's laws seem designed for complexity. Could there be a more fundamental reason, something woven into the fabric of reality that makes life not just possible, but inevitable? String theory, for instance, hints that the constants we observe might not be arbitrary at all, but the only possible outcomes of mathematical consistency in higher dimensions. Others explore the idea of a self-aware universe where consciousness isn't just a happy accident, but a fundamental feature that shapes the laws themselves. It's a radical thought. What if the universe fine-tuned itself because observers like us are part of its ultimate purpose? the Anthropic Principle also forces us to confront the limits of scientific inquiry. Normally, we explain phenomena by tracing them back to causes, but when it comes to the universe's foundational rules, there's no before to point to. The anthropic approach shifts the question from "why are the laws like this?" to "what must the laws be like for us to exist?" It's a subtle but powerful reframing, one that turns our existence into a tool for understanding the cosmos. Think of it like a detective using footprints to reconstruct a crime scene where the footprints and the universe's laws are the scene we're trying to decode. What's fascinating is how this principle connects to the very old human instinct to see purpose in the cosmos. Ancient myths often portrayed the universe as created for life, with gods setting the stars in motion for humanity's benefit. The Anthropic Principle isn't a return to mythology, but it does resonate with that same awe, the startling realization that the universe's order isn't just a backdrop for life, but its enabler. Whether through multiverses, deeper physics, or something beyond our current grasp, the principle reminds us that our ability to ponder these questions might be the most important clue of all. So the next time you look up at the night sky, remember, the fact that you're here to see it isn't just a trivial detail. It's a cosmic puzzle piece, one that challenges us to ask not just how the universe works, but why it works the way it does. And in that question lies the seed of every discovery, every theory, and every leap of imagination that pushes us closer to understanding our place in the grand tapestry of existence. Cosmic mysteries don't just challenge our knowledge, they redefine the boundaries of what we think is possible. Take the Big Bang itself. We can trace the universe's expansion back to a single, unimaginably dense point. But what set that point into motion? Was it a quantum fluctuation in some primordial void, or the collision of higher dimensional brains as string theory suggests? The closer we look, the more the beginning slips through our fingers, revealing a puzzle with no clear edges. Even time, as we understand it, might not have existed before that moment, making the question, what came before? As paradoxical as asking what's north of the North Pole, then there's dark energy, the enigmatic force accelerating the universe's expansion. Imagine blowing up a balloon with galaxies drawn on its surface. Only the balloon isn't just inflating, it's stretching faster and faster, as if some unseen hand keeps pumping air into it. This isn't just a curiosity, it's a cosmic revolution, overturning the long-held assumption that gravity would eventually slow everything down. Yet for all its influence, dark energy remains a ghost. Is it the energy of empty space itself, a new kind of field, or evidence that Einstein's theory of gravity needs rewriting? The answer could determine whether the universe ends in a cold, barren drift or something even stranger. And what lies beyond our cosmic horizon? If inflation theory is right, our observable universe might be a tiny bubble in an infinite multiverse, where other bubbles host entirely different laws of physics. Some could have stronger gravity, making stars burn out in moments. Others might lack electromagnetism, leaving matter forever formless. The idea isn't just speculative, it's a potential explanation for why our universe seems so finely tuned for life. In a multiverse, every possible configuration exists somewhere. We just happen to inhabit the rare pocket where conditions allow galaxies and us to exist. Yet these unanswered questions aren't just gaps in our understanding, they're invitations. Every mystery, from the nature of dark matter to the fate of quantum information in black holes, represents a frontier where chaos and order dance in ways we're only beginning to glimpse. The universe doesn't owe us answers, but it does offer clues. In the faint afterglow of the Big Bang, in the way galaxies spin too fast for their visible matter, in the mathematical symmetries that hint at deeper layers of reality. What's thrilling is how these puzzles connect. Dark energy's acceleration might hinge on the same quantum processes that sparked inflation. The multiverse could explain why the cosmological constant is so improbably small. Even the search for a theory of quantum gravity, a framework to unite the very large and the very small, might reveal why the universe favors structure over chaos. Each question is a thread in a larger tapestry, and pulling one could unravel insights we haven't dared to imagine. So while we marvel at how far cosmology has come, from mythic creation stories to precision measurements of the cosmic microwave background, the greatest gift of modern science might be humility. The more we learn, the vaster the unknown becomes. But that's the essence of exploration, not just mapping the known, but embracing the wonder of what lies just beyond the edge of our understanding. And in that space between mystery and discovery, between chaos and order, the universe keeps its most tantalizing secrets. The universe's fate hinges on a silent tug of war between two invisible forces, the relentless pull of gravity and the mysterious repulsion of dark energy. Right now, dark energy is winning, pushing galaxies apart at an ever-increasing rate. If this continues unchecked, we're headed toward a big freeze, a future so distant and desolate, it makes the coldest reaches of space today seem warm by comparison. Picture a cosmos where galaxies have drifted so far apart, their light can no longer reach one another. Stars burn out, black holes evaporate, and the universe becomes a vast, dark graveyard where even time loses meaning. Temperatures would plummet to near absolute zero, and the last flickers of heat death would mark the end of all activity forever. But dark energy might have an even more dramatic card to play. What if it doesn't just accelerate expansion but grows stronger over time? In this scenario, known as the Big Rip, dark energy's grip would tighten until it overwhelms every force holding the universe together. First, galaxy clusters would be torn apart, then individual galaxies. As the acceleration intensifies, stars would be ripped from their orbits, planets shredded from their solar systems. In the final moments, even atoms would be torn asunder, nuclei split apart by the violent stretching of spacetime itself. The universe wouldn't just fade, it would end in a catastrophic crescendo of disintegration. The difference between these two fates comes down to dark energy's true nature. If it remains constant, as Einstein's cosmological constant suggests, the big freeze is inevitable. But if dark energy is dynamic, a force that evolves or strengthens, then the big rip becomes a real possibility. Some theories even propose a third option, that dark energy could one day reverse, pulling the universe back together in a big crunch where everything collapses into a fiery singularity, perhaps birthing a new cycle of cosmic rebirth. Clues to our ultimate destiny lie hidden in the universe's expansion history. By measuring how fast galaxies are moving apart at different distances, and thus different eras, astronomers can trace dark energy's influence over billions of years. Projects like the Vera Rubin Observatory and the Euclid Space Telescope are mapping the cosmos in unprecedented detail, searching for subtle shifts in expansion that might reveal whether dark energy is constant or changing. Even the cosmic microwave background, that ancient echo of the Big Bang, carries faint imprints of dark energy's early effects, offering hints about how it might behave in the far future. What's haunting is how closely our fate is tied to the same forces that shaped the universe's birth. The quantum fluctuations that seeded galaxies, the dark matter scaffolding that guided their growth, the dark energy now tearing them apart, all are threads in a single cosmic story. The chaos of the early universe set the stage for the order we see today, and now that order is unraveling, pulled apart by the same mysterious energy that once fueled inflation. In a way, we're living in the universe's twilight, a brief window where galaxies still shine and life can exist before the darkness closes in. Yet there's a strange beauty in this grand narrative. Whether the universe ends in ice, fire, or rebirth, its story is written in the same laws that allowed us to exist in the first place. The atoms in our bodies were forged in stars that lit up the cosmic dark ages, and now we're here to witness and ponder the unfolding of a destiny set in motion 14 billion years ago. That's the ultimate paradox. The universe's impermanence is what makes our fleeting moment of awareness so extraordinary. We are the cosmos contemplating itself, tracing the arc from chaos to order, and now watching as order dissolves once more into the unknown. From the moment humans first gazed at the stars, we've sought not just to map the cosmos but to understand our place within it. The story of the universe's birth from chaos isn't merely a scientific puzzle, it's a mirror reflecting our deepest existential questions. If the laws of physics emerged from randomness, does that render life a fluke, or does the very fact that we're here to ponder it suggest something more? This tension between chance and design has echoed through centuries, from ancient creation myths to modern quantum theories, revealing how tightly science and philosophy are woven together. Consider the cosmic coincidences that make our existence possible, the precise tuning of physical constants, the delicate balance between expansion and gravity, the quantum fluctuations that seeded galaxies. Each seems improbably fine-tuned for complexity. Some scientists argue this is simply survivor bias. In a multiverse of infinite possibilities, we naturally find ourselves in one where conditions allowed life. Others see fingerprints of a deeper order, a universe predisposed to create observers capable of unraveling its secrets. The debate isn't just academic, it shapes how we view everything from the value of life to humanity's role in the grand scheme. Spiritual traditions have long grappled with these themes, often framing creation as a battle between chaos and order. The Babylonian Enuma Elish describes a world forged from the clash of primordial gods, while Hindu cosmology speaks of cycles of destruction and rebirth mirroring modern cyclic universe models. Even the biblical notion of light emerging from void finds eerie resonance in the Big Bang's sudden ignition. These parallels don't prove ancient knowledge of astrophysics, but they reveal a shared human intuition that existence arises from some fundamental tension between randomness and structure. Modern physics adds a provocative twist. The universe's apparent fine-tuning might not require a designer, but it does demand explanation. String theory's landscape of possible universes, the Anthropic Principle's statistical reasoning, even quantum mechanics' observer-dependent reality, all blur the line between physical law and metaphysical inquiry. When a quantum particle exists in multiple states until measured, does consciousness somehow anchor reality? The question ventures beyond science into philosophy's domain, where the act of observation becomes as mysterious as the cosmos itself. What's striking is how these ideas transform our sense of scale. A universe born from chaos yet yielding life suggests a narrative arc, not necessarily purposeful, but not entirely accidental either. Like a river carving a canyon, randomness acted within constraints, producing complexity over eons. In that view, we're both insignificant and extraordinary, fleeting inhabitants of a tiny planet, yet products of cosmic processes so precise, their repetition across infinite universes seems unlikely. This duality, humility, and awe might be the most profound legacy of cosmology. The search for origins, then, is more than a scientific endeavor. It's a dialogue between data and meaning, equations and wonder. Whether the universe's order emerged by chance or necessity, the fact that we can debate it at all binds us to the stars in a way no telescope can measure. Our questions about chaos and cosmos aren't just about how things began, they're about why we care, and what that says about the universe's capacity to create beings who long to understand it. The next great leap in understanding our cosmic origins isn't just on the horizon. It's already unfolding, powered by telescopes and detectors so advanced they border on science fiction. Take the James Webb Space Telescope, floating 1,000,000 miles from Earth, its golden mirrors peering back to the universe's infancy with unprecedented clarity. Unlike Hubble, which showed us stunning galaxies, JWST operates in infrared, piercing through cosmic dust to capture light stretched by 13 billion years of expansion. It's like upgrading from grainy black and white footage to Ultra HD, revealing details of the first star's violent births, the chemistry of primordial galaxies, even the atmospheres of distant exoplanets. Every image is a time machine, transporting us to eras when the universe was transforming from a formless void into the structured cosmos we recognize today. But JWST is just one piece of the puzzle. On the ground, instruments like the Vera Rubin Observatory are preparing to map the entire visible sky every few nights, creating a cinematic time-lapse of the universe's evolution. Imagine spotting supernova as they explode, tracking asteroids with unprecedented precision, or catching the faint glow of rogue planets drifting between stars. This isn't just about more data, it's about seeing the universe in motion, uncovering patterns invisible to single snapshots. Combined with JWST deep field revelations, these surveys could pinpoint exactly when and how dark matter's invisible scaffolding began guiding gas into the first galactic structures. Then there's the silent revolution in gravitational wave astronomy. LIGO and Virgo detectors have already opened our ears to black hole collisions, but next-generation observatories like LISA, a space-based trio of satellites, will tune into lower frequencies, capturing mergers of supermassive black holes and possibly even echoes from inflation itself. If the early universe was a stormy sea, gravitational waves are the ripples left behind, carrying undisturbed information from epochs before light could travel freely. Detecting primordial waves would be like finding a recording of the Big Bang's thunderclap, offering direct evidence of how spacetime itself trembled as order emerged from chaos. What makes this moment so extraordinary isn't just the technology, it's the convergence. For the first time, we're combining ultra-deep infrared imaging, real-time sky surveys, and gravitational wave detection to triangulate cosmic history. One tool might reveal how the first stars ionized the universe, while another traces the dark matter halos that birthed them, and a third listens for the gravitational echoes of their formation. It's like assembling a jigsaw puzzle where each piece comes from a different angle, yet together they reveal a coherent picture. The stakes couldn't be higher. These instruments might finally answer why our universe took this particular path from chaos to complexity. Did inflation leave detectable imprints? Are there hidden dimensions affecting galactic rotation? Does dark energy evolve over time? Each question probes the boundary between known physics and the uncharted territory beyond. And with every new discovery, we're not just filling textbooks, we're rewriting humanity's origin story, one observation at a time. The cosmos has kept its secrets for 13 billion years, but the tools to unlock them are now in our hands. From the Big Bang's initial firestorm to the delicate filaments of the cosmic web, the universe has woven a story of transformation, one where chaos and order dance in an endless cosmic rhythm. What began as a seething, formless sea of energy has, over billions of years, sculpted itself into galaxies, stars, and planets, and even creatures capable of contemplating their own origins. Yet for all we've uncovered, the journey feels less like reaching a destination and more like stepping onto a vast, uncharted shore, where every answer reveals deeper questions waiting just beyond the waves. Consider the sheer improbability of it all. The universe could have remained a featureless void, its particles scattered too thin to ever coalesce. Instead, against all odds, quantum fluctuations became galaxies, gravity's patient pull forged solar systems, and the fragile conditions for life emerged on at least one tiny world. Whether this outcome was inevitable or a fluke remains one of cosmology's most profound debates. Some argue the laws of physics are uniquely tuned for complexity, that given enough time, order must arise from chaos. Others contend we're the beneficiaries of cosmic luck, a rare alignment in an infinite multiverse where most universes remain barren. What's undeniable is how fleeting our moment in this story truly is. We live in a golden age of cosmic observation, where telescopes peer back to the universe's infancy and supercomputers simulate its possible fates. Yet we're also temporary guests in a timeline stretching billions of years behind and ahead of us. The stars we see today will eventually burn out, the galaxies we map will drift beyond sight. Even dark energy's grip may one day loosen or tighten, rewriting the universe's destiny in ways we can't yet predict. But here's the wonder, we get to witness it. However brief our chapter may be, we're the universe's way of understanding itself, of turning chaos into curiosity, randomness into revelation. Every observation, from the faintest quantum ripple to the grandest galactic cluster, is a stitch in the tapestry of meaning we're collectively weaving. And as new tools like the James Webb Space Telescope and next-generation gravitational wave detectors peel back more layers, we're not just passive spectators. We're active participants in a story still unfolding. So what do you think? Is the universe's order written into its fundamental fabric, or are we the beneficiaries of an astronomically unlikely roll of the dice? Drop your thoughts below, and if you've enjoyed this journey from chaos to cosmos, don't forget to like and subscribe for more deep dives into the mysteries of space. The universe's greatest secrets are still out there, waiting for the next curious mind